Hi, I'm Rupak Mukherjee. In this work, we have shown that shear Alfven waves can attenuate or decay via scattering from random magnetic fluctuations. Shear Alfven waves are important for both astro as well as laboratory plasmas because it suffers from least decay. In solar coronal region, it can pass through the photosphere and thus can carry the heat from the solar core until the corona. When the wave decay, the energy gets dissipated within the nearby plasma and heats up the medium, thereby increasing its temperature. Interestingly, the viscous and resistive decay of shear Alfven wave does not adequately account for the high temperature of the solar corona. Our proposed alternate mechanism shows that the attenuation because of such stochastic magnetic fields is significantly higher than the attenuation due to collisions. But we consider the linear propagation of a shear Alfven wave in an ideal incompressible plasma that has an equilibrium magnetic field B, which is B0, extended in the Z direction. Wave propagates along the field direction and has field perturbation. So this is the Z, only the derivative on space appear only on Z, and the field perturbations are B and V, small case. We can expand B in terms of B0 and the stochastic part, which is the B0 tilde, and the amplitude of the stochastic part is with the ratio of the stochastic part with the B0 is epsilon, which is a very small quantity. Thus, if we substitute Alfven velocity, which is this, in this equation 1, we get equation 3, which is this, and we can safely ignore the epsilon square terms. This equation 3, this is very important for us because we are going to take a two-pronged approach. One is the analytical solution of this equation 3, and we will find the dispersion relation of the shear Alfven wave propagating in a stochastic magnetic field, and then we will solve this equation directly, equation 3, using PyClop or the ClopX software, which is a well-known software. And we will see how we will compare the analytical and the numerical decay rates. For the analytical solution, we expand this by, the small by, in terms of a mean by, which is the average of by, and a deviation from the mean, which is the by prime. We take the ensemble average of equation 3, which is this, where G is the Green's function, and then we also define R in terms of a correlation length and R0, which is the amplitude of the perturbation. And we take the Fourier transform of equation 5, which gives us this equation, and substitute the definition of R from here in this Fourier transform equation to get the dispersion relation. So in this equation, equation 7, we need to integrate this quantity, and then it will give us the dispersion relation of a shear Alfven wave propagating in a random magnetic or stochastic magnetic field in the Z direction. So this is precisely after doing the integration, we get this quantity, where Z is capital Z. This is the plasma dispersion function, which is this quantity. We can expand this in the two turbulence regimes, which is the short scale length and the long scale length. And it is to be noted that for both the cases, the omega, this varies as k square for both short and as well as long scale length turbulence. This is k square, the decay rates basically, that I. And it goes linearly with R0, which is the amplitude, and the lambda, which is the correlation length. So for both the cases. When we go with the numerics, we see for both lambda as well as for R0, it goes linearly. And in numerics, we start with the by. This is the by in this Z direction. This propagates with time, and we take the Z average of this quantity, which falls off after some fluctuations, and we do some exponential fit, and the coefficient of the fit gives this gamma. And we see that in our analytical results match with the numerical results, both in the short and long turbulence, and also for the k, it goes as k squared here. We also do collisional damping cases for the shear Alfven wave, which goes as k squared. And we see that these results are comparable for RE and RM 10⁴. However, for solar coronal region, this is very high. So we can consider that our cases, which is the decay of shear Alfven wave, because of the random magnetic perturbation, that's more important. That is fundamentally contribute more for the plasma heating case in the coronal region. So our analytical as well as numerical analysis support the result, and it is evident the solution of equation 3, which is this, damps out with time. Thank you for your attention.